Good morning. This lecture addresses propositional equivalences. The question addressed in this lecture is, how do we know when two compound propositions are logically equivalent? We define tautology, contradiction, and contingency, and present common laws and equivalences with examples to enhance our understanding. We concluded with an exercise from our text that is similar to those that are assigned. Definition 1. A compound proposition that is always true, no matter what the truth values of the propositions that occur in it, is called a tautology. A compound proposition that is always false is called a contradiction. A compound proposition that is neither a tautology nor a contradiction is called a contingency. Table 1.1 gives an example of a tautology. The tautology in this case is P or not P. No matter what the values of P or the values of not P are, the value of the compound proposition P or not P is always true. Table 1.2 gives an example of a contradiction. The contradiction is P and not P. No matter what the values of P is or the values of not P are, the value of the compound contradiction, the values of the compound contradiction P and not P are always false. Definition 2. The compound propositions P and Q are called logically equivalent if P, if and only if Q, is a tautology. The notation P triple equals Q denotes that P and Q are logically equivalent. Table 2, De Morgan's laws. We know that the complement of P and Q is equivalent to not P or not Q. And contrariwise, we know that the complement of P or Q is equivalent to not P and not Q. Example 2. Show that not the complement of P and Q and not P or not Q are logically equivalent. This is the first of the two of De Morgan's laws. Solution. The truth table for these compound propositions is displayed in Table 3. Because the truth values of the compound propositions, the complement of P and Q, and the disjunction of not P and not Q agree for all possible combinations of the truth values P and Q, it follows that the complement of P and Q, if and only if not P and not P or not Q is a tautology, and these compound propositions are logically equivalent. So we have showed this in Table 3. Notice that we have all possible combinations for P and Q, and we construct on the left the complement of P and Q, and we construct on the right not P or not Q, and we note that in every case, for every row, that the two compound propositions are identical, satisfying the if and only if condition, and we can therefore conclude that it is a tautology. Table 4 shows the truth values for not P or Q, and P implies Q, and we see that this too is a tautology. Show that P implies Q and not P or Q are logically equivalent. So as before, we build up on the left P implies Q, and we built up on the right not P or Q, and we find that the value for every row is identical, satisfying the condition for if and only if in every case, making it a tautology. Example 4. Show that P or the quantity Q and R and the quantity P or Q and the quantity P or R are logically equivalent. Solution. The truth table for these compound prepositions is shown in Table 5. Notice that we have 8 rows plus a title row, plus of course the table description that describes what we are doing. And we build up on the left P or the quantity Q and R, and then we build up farther to the right P and Q, or excuse me, P or Q and the quantity P or R. And we note that in every case the value is the same, making it logically equivalent. Table 6 has some logical equivalences. We have the identity laws. P and true is always equivalent to P, and P or false is always equivalent to P. We have the domination laws. We have the idempotent laws. We have the double negation laws. We have the commutative laws. We have the associative laws, distributive laws, De Morgan's laws, absorption laws, and negation laws. And we have extended De Morgan's laws, that is, the complement of P1 or P2 or Pn is equivalent to the complement of P1 and the complement of P2 and the complement of P sub n. Similarly, we have the complement of P1 and P2 and Pn is equivalent to the complement of P1 or the complement of P2 or the complement of Pn. So table 7 shows that we have some logical equivalences involving conditional statements. P implies Q is equivalent to not to P or Q. P implies Q is also equivalent to not Q implies not P. This is the contrapositive. We have P or Q is equivalent to not P implies Q. P and Q is equivalent to the complement of the quantity P implies not Q. Not the quantity, the complement of P implies Q is equivalent to P and not Q. And you can see these more complicated ones here below. Table 8 has the equivalences involving biconditionals. The first being P if and only if Q is equivalent to P implies Q and Q implies P. P if and only if Q is equivalent to not Q if and only if not P. P if and only if Q is equivalent to P and Q, or the quantity not P and not Q. And finally, the complement of P if and only if Q is equivalent to P if and only if not P. Example 5.1. Use De Morgan's laws to express the negation of Miguel has a cell phone and he has a laptop computer. Solution. Define the propositions as shown below. Variable P, Miguel has a cell phone. Q, Miguel has a laptop computer. Original, P and Q, Miguel has a cell phone and Miguel has a laptop computer. Negation, the complement of P and Q. Miguel does not have a cell phone, or he does not have a laptop computer, which in logical connectives is not P or not Q. Example 5.2, use De Morgan's laws to express the negation of Heather will go to the concert or Steve will go to the concert. Variable R, Heather will go to the concert. Variable S, Steve will go to the concert. Original R or S, Heather will go to the concert or Steve will go to the concert. The complement is the complement of the quantity R or S. Applying De Morgan's laws, we have not or and not S. Heather will not go to the concert and Steve will not go to the concert. Example 6.1. Show that the complement of P implies Q and P and not Q are logically equivalent by developing a sequence of logical equivalences. Solution. And this is how I would like for you to do your proofs. That is, you have a two-column table, and in the left column you have an expression, and in the right column you have the justification. You begin with the original expression, and you moved from the left-hand side of the equivalent to the right-hand side of the equivalent, and you have to justify every transformation that you make on successive lines. So we begin in this case with the complement of P, complement of the expression P implies Q. Then what we do is we take the example 3 from table 4 and transform that to the complement of not P and Q. Then we apply De Morgan's laws, and we finally end up on the last row, the double negation law, and that arrives at our right-hand side of what we wanted to find. Show that the complement of the quantity P implies Q and P and not Q are logically equivalent by employing truth tables. Two compound propositions are equivalent if their equivalency is a tautology. And we can see from the table below that we do get the equality in every row. Example 7. Show that the complement of the quantity P or the quantity not P and Q and not P and not Q are logically equivalent by developing a sequence of logical equivalencies. We begin with the original left-hand side. We apply De Morgan's law. We apply De Morgan's law again. We apply the double negation law. We apply the distributive law. We apply the negative law, and we apply the commutative law, and finally we apply the identity law to arrive at the right-hand side. Example 8, show that P and Q implies P or Q is a tautology. Solution: to show that the statement is a tautology, we use logical equivalences to demonstrate that it is logically equivalent to true. Note that this could also be done with the truth table. So we take the original expression and we go to table 3 and note that P implies Q is equivalent to not P or Q. So we go ahead and apply that equivalence. We apply the De Morgan's law. We have the restatement removing parenthesis. We apply the commutative law. We apply the associative law. We apply the commutative law again, and we apply the negation law, and we apply the domination law to find that no matter what happens, this statement is always true. Now we go to an exercise that's similar to the ones that are assigned. Use a truth table to verify the associative law. P, the quantity P or Q or R is equivalent to P or the quantity Q or R. Solution: how many rows are needed? Answer: 2 to the number of variables. And since we have 3 variables, that's 8 plus 1 for the title row. How many columns do we need? Let us develop the truth table a step at a time. First, we need a column for each of the propositions.